So today we will have a series of lectures starting with myself and then with Professor Pallab Dasgupta on the topic of complexity, approximation and randomization. And when we talk about complexity, just to recapitulate, and especially in a course like this, which is an introductory course, it is most important that we do not start bombarding them with those great nomenclature, P, NP, union, intersection, infinity, and then write Turing machine, tape moving up, down. They will go to sleep. Facebook. So it is important that we introduce this topic, but then bring in the formalisms at a certain point in time. So when you teach this topic, it is very important that we try to highlight the overall issues and bring it down to them, because they will not have the same topic if taught in a theory course, taught in an algorithms course, and taught in an advanced postgraduate course has got different flavors. So here, since we are concentrating on teaching the introduction to algorithms course, we must first start off with again recapitulating the difference between problem complexity and algorithms complexity. So we all know what is the complexity of an algorithm, order something. We can calculate the complexity of the algorithm to be order something. Now, what is the complexity of the problem? How do we define the complexity of the problem? Size of the lower bound, time taken by the best known algorithm to solve the problem is the algorithm complexity. Number of variables involved. In implementation problem. There is something called the intrinsic complexity of the problem. So how hard is the problem to solve? And this intrinsic complexity of a problem is a very, very well studied and a very deep topic. The intrinsic complexity of a problem starts with the first issue. What is the first issue on the intrinsic complexity of the problem from the algorithm's point of view? Right. Whether it is computable or not. Whether the problem is computable or not. So the first question that needs to be explained to the student is whether the problem is solvable or not. So how will we explain this? How will we explain whether the problem is solvable or not solvable? That the issue, the concept of solvability, that there are problems which are not solvable computationally. First year he has done programming and come, no Turing machine knowledge is available with that fellow. So you have to start teaching a Turing machine first. No, I am telling you, these are important. Nowadays, nowadays it is like students, you have to slowly put it into them. They will all tell you they know everything. Slowly, otherwise they will get disinterested and then they will graduate from your university, go abroad. In 3 years they will tell you how it should be taught, and exactly the way you wanted to teach them they will tell you. So these are all parts of life. We have also gone through this process. So how are we going to explain to a student about the solvability issue?
Excuse me, sir.
Reducing the problem to some unsolvable, वही तो chicken and egg हो गया. What is an unsolvable problem?
Excuse me, sir. Here.
Real numbers. We cannot map real numbers onto integers. And mapping real numbers onto integer is a unsolvable problem.
Mapping real numbers onto integers.
Diagonalization principle.
Mapping real numbers into integers, they won't understand all this.
Excuse me, sir.
By no, these people only know programming. They only know programming. So first thing, yes. Whether? See, first you tell them
Hello, sir.
that why do you have to spend so much time checking whether your program has gone into infinite loop? Why did somebody not write a program to check whether your program has gone into read your program and find out whether this fellow will go into an infinite loop. Otherwise, all our time is spent program infinite loop, control all, del, duck.
So we can tell them that we cannot write an algorithm to be a happy forever. This would be the great
We
example.
cannot write an algorithm?
To be happy forever.
No, to be happy and
You
sad,
cannot,
all these are.
I mean, this would be the simple example which we can convey them
No,
to.
no.
Sir, to explain the deterministic concept,
Huh?
instructions are deterministic solve or not deterministic?
No. First you have to tell them, first statement is, why did people never write a program to check whether a program, they will read one program and whether that program goes into an infinite loop or not. Why did people not write that program? Why do we have to spend so much time? Why? Why? So the first thing is, we have to explain it from first principles. And when you try to explain from first principles, you have to go to the problem that we told them. That means that suppose, why did somebody not write? What is the specification of that problem? That means I want to write a program P that takes as input a program small p, all right? It takes as input a program small p, and p stops if P stops with yes if small p loops, because we want to check whether it will go into an infinite loop. So capital P, or let's call it M. This PP, and then we'll write PPC, and then PPD, and then PDG, and we'll get into trouble. All of us are unsolvable people. let us assume that small p is a program whose input is also given. All the inputs are given initially, assigned in the program itself. So there's for some input, for some fixed input. So why did people not write a program called M, which would read another C program called P, and this M would have the property that after some time it would stop and print yes when P would go into an infinite loop, and otherwise after some time it will stop and print no if P does not go into an infinite loop. No, no, no. We are saying that such a program M exists. No. Who said it doesn't exist? To the first student who is sitting in your class, if you tell him that von Neumann told it does not exist, that is one way of telling people, you know. We have to slowly convince them. So suppose M exists. Then M is a C program. So I will say, okay, give me M. Give me the code for M. So he says, okay, I can write M. So I will give him the code for M. So I will look at the code for M, and wherever he has got print yes, what will I do? Wherever he has got print yes, I will replace that part of the print yes, and before that I will write return. Stop. So what will I do? I will take M and make my own program, M dashed, which will say M dashed stops without printing anything if P loops. And the place where it prints no, I will replace it by while semicolon. What is while semicolon? Infinite loop. I will replace it by while semicolon. So what will happen to M now? M dashed loops if P stops. So if M exists, then M dash also exists. Correct? Now what is the killing argument? The killing argument is M dash works for everything. So it also works for M dashed. So what happens? This is what happens. What does this mean? This is a contradiction. So M dash does not exist. So M does not exist. That is a simple program to write, to find out. So this is all about your halting problem of Turing machine. Have you understood? This is all that great halting problem of Turing machine is this. It's all about it. You explain to them in C language. Now once this is explained, then you know they will get a little excited. Then you become a little more courageous. And this argument which we just gave, when we put M dashed as the input, is called the What argument? It is called the diagonalization argument. It is called the diagonalization argument. So now we will explain. So now slowly we will get a little more into the math to explain the diagonalization argument. So to explain the diagonalization argument, how will we go ahead in doing that? We will say that every program that you can write, never talk in terms of Turing machines till you get them all captured, and then they have nowhere to run, then you start Turing machine. But first we need to capture their attention. And therefore, you say that let us list out all programs in the world, P1 to infinity. So there can be all programs in the world and label them P1, P2, P3, P4 up to P infinity. And prepare all inputs in the world x1, x2, x3, x4 up to infinity. And then create a table of P1, P2, P3, P4. This is an infinite table on the number of rows, and then x1, x2, x3, x4, and so on up to infinity. And assume that these problems P1, P2, P3, P4 on x1, x2, x3, x4 terminate by saying yes or no. They terminate by saying yes or no. So they are all decision problems. So now I have this world's all problem table where the yes no answers are all given. Yes, no, no, yes, no, no, yes, something like that. And so on. So this means that I have this table which has all the programs in the world, and obviously all the programs in the world, because programs are finite sized, programs are all finite sized, so they can be mapped to integers. That is why I infinite set but mapped to the integer set, positive integer set. Similarly, inputs are of finite size. They can all be sorted out and numbered. Some numbering scheme you can do, lexicographically sort them, do whatever, and number them. And then you say that I will create a new input. How will I create a new input? I will look at the diagonal and I will create. So every input output is a new problem. A problem is defined by a row like this. For this input, this is the output. This is how the problem is defined. A problem is defined by saying for this input, this is supposed to be the output. So I now define a new problem. How do I define? I look at this. If this is yes, I write no. If this is no, I write yes. If this is yes, I write no. If this is no, along the diagonal, I write yes, and so on. Look very carefully. Along the diagonal, I make a new, I look at it and I make a new input. And after making this input, what is the claim that I make? That this row does not exist in that table. I make a claim saying that this new row that I have created does not exist in the table that I had formed. Are you okay with me? Which means that there is this problem which does not exist in the list of all solvable problems. This is the other way to place the diagonal argument. Then I come to the point that you just said. How many such problems are there? You will, by looking at this, the student will say, I have only one such problem. How many such problems will be there? Infinite is a very simple word. You know how many infinities are there? Is there only one infinity? No, I am serious. Is there only one infinity? Is there an infinity larger than another infinity? There is. There is. Which infinity is larger than which infinity? Tell me. As he just said, the set of real numbers is infinite and the set of integers is infinite, but the set of real numbers is a strict superset of the set of integers. Next question, is there something bigger than the set of real numbers? There is an infinite hierarchy of infinities. Let us, after some time, let us stop, otherwise we'll get into God and things like that, but it's okay. So, if you simply look, instead of doing this diagonal, if you did this diagonal, you would have got another input. If you did it this way, you have got another input. Actually, if you permute this x1, x2, x3, this set, for every permutation you take the main diagonal, you will get one more problem like this. So, the number of unsolvable problems is at least the number of permutations of x1, x2, x3, x4 up to infinity. That is the number of permutations. So, suppose I take an infinite set of an integer infinite set, and I take all permutations of that. What is the set formed? The set of integers, and I form sets by taking how many permutations can I take of the set of integers? The power set. The power set of the set of integers is the set of reals. The power set of the set of integers is the set of real numbers, which means that the number of unsolvable problems, the ratio of the number of unsolvable problems to the number of solvable problems is in the ratio of the size of the reals to integers. So, after you say this, like all of you have become silent, they will become silent. And then you can start slowly teaching them. So, next we come to the set of problems that are solvable. But among the problems that are solvable, you can give them dangerously bad problems. You can tell them, write a program to print the value of pi. Go on printing. What is the complexity of this problem? And what is the complexity of this algorithm? No, it is solvable. You are printing. Yeah, it just goes. So remember that a problem's complexity is determined not only on the input size, but also on the output size. So if the output size is infinite, and you go on printing, it does not matter. Your problem may be order n complexity. So that is not what we are talking about as a hard or difficult problem. For example, you know the Tower of Hanoi's problem. All of you know how to solve Tower of Hanoi? How do you solve Tower of Hanoi? We Indians call it the Tower of Brahma. You know why? You know why we call it the Tower of Brahma? No, why do we call it the Tower of Brahma? All of you know the Tower of Hanoi's problem, no? That there are these 3 pegs and there are these n discs, and you have to move them from A to C using B, and never should a smaller disk lie below a larger disk. So how many steps are required to move n pegs from 2 raised to the power n minus 1? And what is the solution? TOH A to B via C. For that, what do you have to do? An n, sorry. Then what do you have to do? If n is equal to 1, then you solve, move A to C. Else? TOH then correct? Sorry, B, A, C. Sorry. And you can prove by induction that this is 2 to the power n minus 1, because it is Tn is equal to 2 Tn minus 1 plus 1. What happened? I am going from A to B via C, and then I am going from B to C via A. So the story goes that, end of the world. The story goes that Lord Brahma does nothing except solve the Tower of Hanoi problem. He has these 64 pegs, and he transfers this from this side to this side, and when transfer is complete, then there is pralaya. And in one day of Brahma, he moves one disk. 1 day of hours, he moves one disk. So approximately somebody has calculated, and I don't know the truth of it, because once you bring in Brahma, Vishnu, Maheshwar, everything becomes true, you know. And if you say it is not true, then somebody will come and hit you. If you say it's true, then somebody else will come and hit you. But this problem, if you say, what is the complexity? We know this is 2 to the power n. Is it 2 to the power n? because your output is also of 2 to the power n size. So it is sensitive to the output. It is actually order n complexity if you take the output into consideration. If you take only input into consideration, it's different. But if you take output into consideration, because that is what you have to produce. So the problem, algorithm complexity, as has already been discussed, is to be counted as the computational complexity, not the complexity to read the input and write the output. The inherent computational complexity. For example, if somebody says, what is the inherent computational complexity of finding out the minimum of n numbers? Can we not argue and say that if you have to do it by comparison, then you must require n minus 1 comparisons? Why? Because any comparison will lead to that comparison tournament tree. And if you can show that no tree with n leaves, if you have less than n minus 1 comparisons, then somewhere you are not comparing somebody. This is a loose argument. Similarly, there are arguments to show that sorting cannot be done by comparison in less than order n log n complexity. Have you seen that proof somewhere? Huh? It is there. Find out. And when you don't know the answer, you tell the students to find out. Good students will find out. And then you look at it seriously and say, okay, good, well done. And there are students in the IIT system who will catch this and write a wrong answer and post it on Facebook and say, yes, said good. So apply all these tricks only when you are going to teach teachers. So at this point in time, when we have talked about sorting, searching, etc., we will come back to an intricate problem like the stamps problem. You know the stamps problem we have discussed? That there is a set of stamps and a value C, and we want to find firstly whether there exists a set of stamps which gives exactly value C, and the second phase we want to find the minimum number of stamps. The first problem is equivalent to, as somebody pointed out, the subset sum problem. That is, given a set L of integers and of integer value C, does there exist a subset of this set whose value is equal to C? Is that clear? Now, this problem is very intriguing because this problem, though looks very simple, does not have an easy solution other than a branch and bound solution or a dynamic programming solution. Which means that if we try to obtain a polynomial time solution, we are not able to obtain a polynomial time solution for this problem. A polynomial time solution, as you know, must have a complexity of order n to the power k for some constant k. So the subset sum problem, listen very carefully, the subset sum problem is very intriguing. It does not, so what is the subset sum problem? You are given a set of integers S, L is equal to x1, x2 up to xn, and an integer c, and you really want to know whether, first version, the simplest version of the stamps problem is, you want to know whether there exists a subset of L whose sum of values is equal to C. Whatever you try, we can write a recursive definition, we have done this, inclusion, exclusion and all that. But no algorithm exists to show that this problem is solvable. No polynomial time algorithm exists. N to the power k, where k is a constant, that is our polynomial time complexity. Order n to the power k for a constant k, no algorithm exists till now. On the other hand, nobody is able to prove that this problem cannot be solved in polynomial time. So this is the nature of this problem. Any other property of the problem? So before you get into Turing machine and deterministic, non-deterministic, these are, you will get into that slowly. But before that, there is another property of this problem. What is it? If a solution is given, then it can be checked in polynomial time. If a solution is given, then it can be checked in polynomial time. So these are the three properties that we find for this problem. The first property is that there is no polynomial time algorithm. Second, that there is no exponential time lower bound proof. And third, if you give a solution, then whether that solution is a correct solution or not can be checked in polynomial time. Then what people figured out is that this problem is not alone. This problem is not alone. So the first problem was, is there a subset S of L such that sigma Si is equal to C for all the elements? That was our question. Correct? Now we define another problem which looks intricately similar to this problem but a little different. Can L be partitioned into L1 into, let us say, M and N such that sigma Mi is equal to sigma Ni that is, given this set, can I partition it into two equal halves such that the sum of this subset and the sum of this subset are equal? This is another problem which has the same features, that there is no polynomial time algorithm, there is no exponential lower bound, and if you give the solution, it is very easy to check whether this problem is solvable in, whether this is a solution or not. The more important thing is 1 and 2 are also intricately related to each other. How? By saying that if I can solve problem number 1 in polynomial time, I can solve problem number 2 in polynomial time. And if I can solve problem number 2 in polynomial time, then I can solve problem number 1 in polynomial time. How do we show that? Suppose I say that I can solve problem number 1 in polynomial time. Then how will I show that I can solve problem number 2 in polynomial time? Tell me. How will I have to show that if I can solve problem number 1 in polynomial time, then I can also solve problem number 2 in polynomial time?
L dash is a set that is excluding the elements that was considered for the first problem, and I see that again I get the value of C. So from L dash I am again checking C, for which I already know the solution.
What I have to do is, I will take any arbitrary instance of problem number 2 and very easily convert it to an instance of problem number 1. How will I do that? Give me any instance of problem number 2. So you are going to give me L and ask whether it can be partitioned into 2 halves. What will I do? I will first sum up x1 to xn and get some capital X. I will define C equal to x by 2 and call the first problem. Got it? Have you got it? I will first, in order n time, I will add the values of L1, x1 to xn and find capital X. So I will find out sigma xi equal to x. I will find this out in order n time, and then I will set C equal to, because if x is not even, answer is no. If x is not even in 5 minutes, you can say answer is no. X has to be even for a partition to exist. If capital X is not even, partition will not exist. But if capital X is even, you set C equal to x by 2 and call and then say that if you had a polynomial time algorithm to solve problem number 1, now you have a polynomial time algorithm to solve problem number 2. And this reduction, this is called reduction. This reduction also has to be done in polynomial time, otherwise it won't work. If the reduction takes exponential time, then your argument that if problem number 1 can be solved in polynomial time, 2 can also be solved will not work. So this transformation also needs to be done in polynomial time. Let us take it the other way around. Says, no. I can solve the second one in polynomial time. Then what will you do? Then what will you do? Listen very carefully. I will first find out x. I will check whether C is more than half or less than half. Okay. I will check, are you okay? I will find out what is. So I am going to now take an instance of problem number 1 and reduce it in polynomial time to an instance of problem number 2. So now I have got L and C. Now what am I going to do? If I solve the partitioning problem of L, I don't solve this problem. So I have to convert the problem. So I will first check, I will find out x, which is sigma xi. Listen very carefully. Listen very carefully. I will find sigma xi. And after I have found sigma xi, I will check whether C is greater or less. Correct? Then, suppose C is greater than half of x, that is C is greater than or equal to x by 2. Suppose capital C is greater than or equal to x by 2. Now what will I do? I will define y we have assumed that if C is greater than equal to x by 2, then compute y. Are you all with me? Then define L dashed equal to L union y. Call this small y, union y. That means into L I add this element y. And I ask, is there a partition? If there is a partition, then one partition will be of size what? C. Because now x plus that y value is equal to twice C. What have I done? I have made sure that x minus C is equal to y. So now I am adding that y. So one half will be C and the other half will be the rest of elements plus y. Is it? Got it or no? Is it this or is it C minus x by 2? This should be y is equal to C minus. See, for the remaining half, I had, when C is greater than x by 2, then C crosses half of x by 2. So now what I want to make is, I want to add one more element such that the whole sum becomes 2C. Correct? In order to make the whole sum 2C, I want to add an element of what size? 2C minus x. This element I need to add. I need to add an element of size 2C minus x. Yes or no? Let me explain again. We have L equal to x1, x2 up to xn. Capital X is equal to sigma xi. I have C and I know C is greater than equal to x by 2. Correct? So now I want to create a new instance L dashed whose sigma is 2C. Okay? Whose sigma is 2C. So how much do I have to add? You want to take an example? Okay. So let us take an example L is equal to 5, 3 and 7 and C is equal to 8. And I want to solve this problem. So I will add, so C 8, how much is sigma, what is x? What is x? Oh, 15 does not work. Yeah, 15 will work, fine. 7, x is 15. So now I will say, I will add an element of size 1 to this set. 1, where did I derive 1 from? 2c minus x. 2c minus x is how much? 1. So I add an element 1 and make a new set 5, 3, 7, 1 and ask if there is a partition. If there is a partition, because I have made the sum 2c, there will be a partition of size c. So if I solve that problem, I will solve this. There can be the other case where c is less than x by 2. There can be the other case where c is less than x by 2. Then what will I do? I will have to add something else. Not remove some elements. If I can remove, I will add one more element in such a way that not negative, positive element. I will add positive element. I can add one more element and make another set and show that by this partitioning, by solving the partitioning problem, I will solve it. So you can take the two cases, you just work it out sometime. Purposely I am not doing it. You have understood the first case, right? The other case is when c is less than x by 2. When c is less than x by 2, what will you do? How much will you add? How much will you add so that you can pack it up? So you figure out, or otherwise you look at any textbook. What? X minus c. He says you add x minus c. X minus c. He says you add x minus c. Then what becomes the total size? It was x, now it becomes previously we had x and we added 2c minus x, we got 2c. Now L dash, if you add x minus c, what will happen to L dash? 2x minus, what do you want actually? X minus 2c, if you add, what will happen? Then it will become 2x minus 2c. Then each partition will become x minus c. Will x minus c adding help? Will x, so okay, so let's change it. X minus 2c. X plus 2c. Huh? X minus 2c. if you add x minus 2c equal to y, if you add x minus 2c as y, then in L dash, what is the sum of the elements? Twice x minus c. It is x plus x minus 2c. So it will become twice of, and then if you partition it, you will get x minus c and x minus c. How will you extract out? L minus if you do this,
So if we do this, each partition will have value capital X minus C.
yes, each partition will have value x minus c, x minus c.
And now our L has total value capital X.
L has total value capital X.
So whatever is there in L except in one of the partitions will have value C.
Right. The partition which has this new element will have the value. The new element is how much? X minus 2c. So the partition which has the new element, the rest of the sum will be how much? If the total is x minus c and the new element is x minus 2c, then the remaining amount there will have to be c. See? So again, by a polynomial time reduction, I have shown that these two problems are intricately related to each other. That if one of them has a polynomial time solution, so will the other, and if one of them cannot be solved in polynomial time, so cannot be the other. And then people started, and each of these had this property that it is neither has a polynomial time solution nor has an exponential time lower bound, but if you give a solution, you can check it. And then slowly, slowly this brotherhood started growing. This brotherhood started growing, and people started showing different problems one after another and started relating to each of them. And then Stephen Cook came, and then he took up a very interesting problem. Stephen Cook took up a very interesting problem. He says that there are a set of Boolean variables x1, x2 to xn. And there is an arbitrary Boolean formula f. There is an arbitrary Boolean formula f. And you want to know whether there is an assignment of 0 and 1 to x1 to xn such that the formula becomes true. This is the famous satisfiability problem. This is the famous satisfiability problem. So a formula can be any type of a formula, arbitrary formula. And so on, some arbitrary formula. Given any arbitrary formula of length L, is there an assignment on the variables which will make the formula true? This problem again did not have a lower bound, did not have a polynomial time solution. And if you give an assignment, it can be checked in polynomial time whether the formula is true or not. So this satisfiability problem was a problem which he showed converts all these problems of this brotherhood. Any problem in this brotherhood can be converted to this satisfiability problem. This brotherhood, they are like these two brothers we got. So there was a big club. And it showed that any problem in this big club can be converted to this satisfiability problem. So the question comes, how do you define this club? How do you define this club? And in order to define this club came the definition of the class NP. The class P is the set of all problems, not algorithms, is the set of all problems who have algorithms for solving those problems in polynomial time. Then he defined this class NP. What is the full form of NP? Non-deterministically polynomial. What do you mean by non-deterministically polynomial? You can't predict the output. No.
The problem can be solved in polynomial time.
What do you mean by the algorithm is non-deterministic?
Sir, it means that if I give the example of DFA and NFA, so the way NFA works, it is non-deterministic and DFA is deterministic.
These fellows, as I told you, don't know DFA and NFA.
For example, sir, another example, suppose we want to sort, it is like branch and bound. If we can take all the branches at a single stroke and travel them, then it is a non-deterministically polynomial time algorithm.
I know that non-deterministic Turing machines, all of you know. And you all know what it is, how you can define the class NP, all that we know. But to tell these people, we have to tell something else. You tell them that in addition to your programming language, I will give you a magic function called choose. In addition to your programming language, I will give you a magic function called choose, which returns 0 or 1. And if you call it, and if the answer to the problem is to be given yes, and if 1 is to come, it will come. So I have a function choose, which somehow tells me, it knows when to tell me what is the correct choice to give. So along that branching, somehow that fellow knows which is the correct branch to take. So you augment your programming language by this choose. For example, in the SAT problem, you will write a program for I equal to 1 to n, Li equal to xi equal to choose I. So for the SAT problem, I'll write for I equal to 1 to n do xi equal to choose. And it will return 0 or 1. And then whatever I get 0 or 1, I will then verify f on x1 to xn, on this choice of x1 to xn. Because if somebody gives me an assignment, the property of this class of problems is such that I can check it in polynomial time. So which means that if I am given a non-deterministic choice function in addition to my programming language, then using this function, I can write out the solution to this problem in polynomial time. I'll show you how we will do the subset sum. I will, for every xi, I will choose. If it comes 1, I will put it in the subset. If it comes 0, I will not put it in the subset. And I am assuming that it will give me the right choice always, such that if there is a solution, it will give me that set for which the sum is equal to C. This is what is meant by non-deterministic choice. This is what is meant by, in that Turing machine, when there are two labels going out with the same label. In a what is the difference between a deterministic Turing machine and a non-deterministic Turing machine? In a deterministic Turing machine, at any state, no outgoing edge, two outgoing edges never have the same label. But in a non-deterministic Turing machine, two outgoing edges can have the same label, and you are saying that it is polynomial time in the sense that I will always choose the correct label to reach my accepting state. Isn't it? That is the definition of a non-deterministic Turing machine. So that is all put into this language, into this choice function. I have added this choice function and made your programming language a non-deterministic programming language. The same for the partitioning problem. Same for the Hamiltonian cycle. You know the Hamiltonian cycle problem? In a graph, whether there is a cycle covering all the edges, you will look at all the edge set and you will choose. There are n square edges. So you will choose whether this will be there or not. And if there is a Hamiltonian cycle, it will give you the choice. And once you get the choice, checking whether it's a Hamiltonian cycle or not is easy. So the set of all problems that can be solved by a non-deterministic Turing machine in polynomial time is called the class NP. Technically, we are supposed to find a non-deterministic polynomial time algorithm. One way of showing that is, you can make a set of non-deterministic choices and verify. Correct? You can make a set of non-deterministic choices and verify. That's the first level way to look at it. It's a little more complex than this. Suppose I tell you, back to that subset sum problem. Back to the subset sum problem, and suppose I tell you that you are to find the minimum number of stamps to get a value C. How will you show that this problem is in the same brotherhood? If I tell you, find whether there exists a set of stamps whose value is C, you can do. Whether there, so next, this we can all do. The other thing we can do is, whether there exists a set of K stamps for which the value is C. That also we can do. Non-deterministically choose k stamps and check whether the value is C. Now if you can do this, then vary k from 1 to n. The first place where you get yes, that is the minimum number of stamps. Got it? So you have to write a complete non-deterministic algorithm using a choice function like this. And then Stephen Cook proved that any problem that is written in the class NP, that is any problem that is written by a non-deterministic Turing machine and has a polynomial time solution, can be mapped to the SAT problem. Can be reduced in polynomial time to the SAT problem. Which means that if the SAT problem is solvable in polynomial time, this whole brotherhood is solvable in polynomial time. And that is why the SAT problem was the first NP complete problem. An NP complete problem is in NP. That means there is a non-deterministic polynomial time solution to it. And it also means that every other problem in the class NP is reducible in polynomial time to it. All right. Now, once you had the first problem, then finding the next problem was easy, because now Stephen Cook has done this hard work of converting all the problems to SAT. Now, all you now need to do is take SAT and reduce it to the new problem. Then you get another NP complete problem. And once you have two NP complete problems, third one can be brought by reducing any one of them. So slowly this class of NP complete problems grows and is defined like this. What is the definition of an NP complete problem? P is an NP complete problem if 1, P is an element of NP, and second, right, there is a polynomial time reduction from a known problem Q of the class NPC to P. Which means that there is a full back chain, that if this fellow can be done, then across the chain you will go back to the SAT problem, and from the SAT problem you know everybody else can be done. Correct? The heart of it lies in these 2-3 concepts which have to be taught. One is the concept of reducibility, polynomial time reducibility between problems. You have to be very careful how you do the reduction. Second is this whole concept of non-deterministic polynomial time. And we have to explain it to the students in multiple ways. If we only tell them non-deterministic Turing machine, it will not work. You have to teach them in the programming language style, non-deterministic Turing machine style, guessing style, 3, 4, then they will get an idea. And then you formalize it into the Turing machine concept. So if only the second property is satisfied, then the problem is known as NP-hard. That is the NP-hardness property. Can you tell me a problem which is NP-hard but not NP-complete? Halting problem is undecidable. It is harder than hard. Traveling salesman problem. When it's not a decision problem,
What is the minimal result? Suppose if you give me a solution, unless I know the minimal one, I cannot really verify the given solution is
why?
Pardon?
Why?
Because to enumerate the minimal
So,
solution.
so
itself
you
takes
can at
action
least,
of-
you can, let me, he says the traveling salesman problem you all know. So you've got a graph with nodes and edges, and you want to find the minimum cost Hamiltonian tour. And he says this is NP hard, let us all accept. But he's saying that this is not in NP. Why?
Unless I know the minimal answer, suppose if you the proposed solution is, you are telling that is the minimal, unless I enumerate all the solution space, I cannot verify your solution is the minimal or not.
That is because you could not do it. That does not mean it does not exist. Okay, so it is defined for a decision problem. So for given any value k, I can solve the problem whether there exists a Hamiltonian tour of cost less than equal to k. This is in NP though.
Yeah.
This is in NP.
Yes.
Everybody okay with him? He has agreed that this is in NP. You have also agreed. Decision problem. So this problem is in NP. Which problem?
Decision version of TSP.
Decision version of TSP. If I give you k, does there exist a Hamiltonian cycle of cost less than equal to k? Done? Good. Now listen to me very carefully. I will first take and sum up all the edges in the graph. Let that sum be S. I will call the decision problem on S by 2. If the answer is no, I will do binary search. I will call it from S by 2 to S, 3/4 of S by 2. No, I will call this side. So, in log n steps, I will know the answer. And if the sum of the numbers is some number, and that is a number, if that number is whatever it is the number, log n of that is obviously a polynomial. So who said it cannot be done? It can be done. You have to be very careful. So the question again I ask, which is the NP hard problem, which is not in NP? Second problem I will ask, which is the problem which has got lower bound exponential time? We have talked about unsolvable and we have talked about NP complete. Does it mean that there is no problem in the world? Huh? Regular expression? Two regular expressions? Comparing two regular expressions is NP hard. Sure. When you don't know the answer and think that person doesn't know the answer, you ask, you know. Two regular expressions is just equivalent to checking equivalence of two finite state machines. Equivalence of two finite state machines is very simple. You minimize both of them. A regular expression is a finite state machine. Yes or no? You can minimize a finite state machine. And what does your equivalence theorem tell you? Two finite state machines which are identical, their normalized canonical forms are identical. There is a little difference there. There is a problem, but it's not comparing two regular expressions. So please find out. But the crux is that this class, NP, and its relationship to P is the most intriguing problem in computer science. We really don't know whether any of these problems are solvable in polynomial time, because if anyone is, all of them are. And if anyone is not, then none of them are. Which means that if any one NP-complete problem is solvable in polynomial time, then P is equal to NP. And if any one of them has an exponential lower bound, then all problems in the NP-complete class have exponential lower bound. So my lecture is also complete.